Okay, welcome everyone. Thank you so much for joining us. Professor Sa is going to be talking about supersymmetric W-algebras. Feel free to start whenever you're ready.
Okay, thanks for inviting me and also introducing me. Today I'm going to talk about supersymmetric W-algebras. So actually, I should say that to be precise, I have to write nk is equal to 1. So I think there is n is equal to 2 supersymmetric algebras for physicists, not for mathematicians, I guess. So what I want to say today is what is supersymmetric W-algebras in terms of vertex algebra language. So let me explain outline first. First part of this talk is about supersymmetric vertex algebra. It is introduced by Helwani and Katz in 2006. So basically, I guess physicists want to say it is already known, but for me, like very mathematician, it was not clear what is supersymmetric vertex algebra. But in this paper, I could find very precise definitions and properties and so on. So you can look for that. And then I will introduce nk is equal to 1 supersymmetric W-algebra, which is introduced by Madsen and Ragusea in 1994. They introduced this algebra by supersymmetric quantum Hamiltonian reduction kind of thing. So I will introduce, not in their language, but in terms of supersymmetric vertex algebra by Helwani and Katz. And then I will explain more about supersymmetric W-algebras. Okay. So what is supersymmetric vertex algebras? There are actually two kinds of supersymmetric vertex algebras. So as far as I know, in most of physics papers, they only deal with this one. I should not say they only, but I think I can say like most of papers are written about like nk, supersymmetric vertex algebra. But I want to explain in like math papers, there are n sub w and n sub k supersymmetric vertex algebras. So later on, I will briefly explain what are differences between these two kinds of supersymmetric vertex algebra. But anyway, so let me explain what is supersymmetric vertex algebra. So it is actually a vertex algebra. And this n here implies the correspondences between even element and odd element. So if you have one even element A in V, there should be n odd element in this vertex algebra. So here, this n comes from here. And similarly, if you have an odd element in V, there should be n even elements. And I will write down like d to the a1 of a, d to the 2 of a, and d to the n of a. And this n sub w and n sub k depends on the operator of operator d to the I. So let me explain a little bit more. So the reason people consider n sub w and n sub k SUSY vertex algebra, it comes from the theory of superconformal Lie algebra. So I should say I'm not an expert of superconformal Lie algebra theory, but at least I can say something about it. So let me explain first what is superconformal Lie algebra. So it consists of L and F, and L is Lie superalgebra, and F is a finite family of Fulmor distributions. And here L is spanned by the coefficients of this formal distributions, and F should contain Virasoro formal distribution. I guess everyone here knows what it is. And we also assume that every pair in F is pairwise local. And the commutator between these two formal distribution has some kind of coefficient, and this coefficient should be in the derivatives of this F. And we also assume this L is kind of a simply superalgebra. So let's say this kind of couple is called superconformal Lie algebra. Then there is a complete list of superconformal Lie algebra, and this consists of 3 types of Lie algebra: W type, S type, K type. And actually, if you have a superconformal Lie algebra, you can find the vertex algebra from this Lie algebra. So I guess the process from superconformal Lie algebra to this vertex algebra is almost same as you get from Lie conformal algebra to like universal enveloping vertex algebra. So mathematicians, I think they first consider this kind of vertex algebra, which comes from superconformal Lie algebra. Then observe what is the translation operator in this kind of vertex algebra. And if L was W type or S type, you get translation operators. This one is the usual translation operator, and this one is odd translation operator. So theta to the I is odd invariant, indeterminate. And for K type, you will get a little bit different kind of odd derivation. So you have to remember this. So depending on these translation operators, they divide this vertex algebra into 2 types, which is W type and K type. So this is kind of idea of L sub W and L sub K. So now I can say something that I know. So let's say, let's see what is N sub K supersymmetric W algebra, supersymmetric vertex algebra. So as you can see, the definition is quite similar to ordinary vertex algebra. So this V is vector superspace, and you have also vacuum vector, which is even element, and this D to the I is odd endomorphisms. So here I should be from 1 to n. And there is a state field correspondence Y. So as usual, I will write it by Y. And this is parity preserving map. And for this capital Z, I will say that this is a tuple of even variables and odd variables. This is odd variables. And SUSY vertex algebra has vacuum axiom and translation covariance and locality. So here everything is almost same, but you should be careful with this translation covariance. So you can see this derivation, which was from the K-type superconformal Lie algebra. And then one remark is that this one, which makes everything a little bit complicated. So usually in ordinary vertex algebra, T of A, T is just the even derivation, is just like this. But here you can see the difference between this part and this part. So this thing makes some little bit makes some difficulties, but it is fine. And this is a notation. So you have products. So n is in integer, and j is a subset of this set. And here z to the minus n minus 1, let's say I, which is I1, I2, Ik, is just small z to the minus n minus 1, and theta to the I1, theta to the I2, theta to the Ik. And assume that I1 is less than I2 and less than Ik, something like this. Okay. Then the problem is we don't know if actually we can get some supersymmetric vertex algebra. Always when you do vertex algebra theory, we need some like good examples, how to construct good examples. That is the problem. And one way is you first consider Lie conformal algebra, which is way simpler than vertex algebra, and then consider the universal enveloping algebra of Lie conformal algebra, and then you get finally some kind of like the most kind of simple, not simple vertex algebra, but simple types of vertex algebra. Anyway, so let me introduce what is Lie conformal algebra. So Lie conformal algebra, SUSY Lie conformal algebra has the n odd derivation and one even derivation. And here you have the commutator relation. So di dj plus dj di is 2 times delta ij of t, and t commutes with any other derivations. And here you have a super algebra consisting of some even variable and odd variable. But here the commutator relation is a little bit different from this quality here. You see the sign difference. I should say the difference of this sign comes from here. So here, if you consider the square of this operator, then you will get minus d sub z. But here, if you consider the square of this operator, you will get like d sub z. So that is why you need 2 different kinds of algebra. And then you will get definition of SUSY Lie conformal algebra. But before you define SUSY Lie conformal algebra here, you need this capital lambda bracket. And this capital lambda is just something like this. And I think if you know what is Lie conformal algebra, it is not hard to follow this definition. You will denote like A sub capital lambda of B. And here, this part is for the part in this Cali L. And here, you put this A sub n of j, and then B. Okay. And then there is sesquilinearity, which is similar to the sesquilinearity of vertex algebra here. You have to be careful with your signs, but without sign, almost same as the usual Lie conformal algebra. And then you will have a skew symmetry also, and Jacobi identity also. And the basic example is Nouveau-Schwarz Lie conformal algebra. So Nouveau-Schwarz Lie conformal algebra consists of one generator here. And this lambda bracket will look like this. So, and now, since you have what is SUSY Lie conformal algebra, you can define SUSY vertex algebra in terms of SUSY Lie conformal algebra. So SUSY vertex algebra should be SUSY Lie conformal algebra, and it should be unital, quasi-commutative, and quasi-associative differential algebra. You will know what is the derivation for this differential algebra. And for quasi-commutativity and quasi-associativity is actually not very simple, but if you know what is the definition of vertex algebra in terms of Lie conformal algebra, you can recover very easily. So for example, here, if you remember what is quasi-commutativity in vertex algebra theory, it was like left-hand side is same, but the right-hand side is something like P of B and J factorial. And I guess sorry, I missed this part. So we should minus 1 plus J. But instead of this part, it was the quasi-commutativity of vertex algebra. But instead of this one, you will just substituting this operator, this binary operation. So this is how you get quasi-commutativity. And for quasi-associativity, I didn't write it, but it is almost same. So if you remember what is quasi-associativity in vertex algebra, then you will just substitute kind of A of n b, A of n b to A n b, something like this. Okay, so you know how we get SUSY vertex algebra from SUSY Lie conformal algebra. Now I want to introduce a little bit about SUSY Poisson vertex algebra. So SUSY Poisson vertex algebra is easier than SUSY vertex algebra. So in the previous definition, if you replace this part, quasi-commutativity, by just commutativity, and quasi-associativity by associativity, and weak formula by Leibniz rule, then you will get SUSY Poisson vertex algebra. And yeah, this part is actually important. So when you have SUSY Lie conformal algebra, if you consider supersymmetric algebra, then you can define the bracket on this supersymmetric algebra by Leibniz rule. And indeed, this becomes a SUSY Poisson vertex algebra. And also, if you have SUSY Lie conformal algebra, you can define universal enveloping supersymmetric vertex algebra. And in this vertex algebra, you can compute your bracket using this weak formula. So you can recover all the brackets between all the elements in this SUSY vertex algebra. And also you have SUSY vertex algebra. In your SUSY vertex algebra, you will have PBW basis theorem. So I should say theory in SUSY vertex algebra is really similar to the ordinary vertex algebra theory. So now, to make everything very simple, I want to consider only nk is equal to 1 case. So what is the most important example? I should say it is SUSY affine vertex algebra. So in order to explain what is SUSY affine vertex algebra, I have to first introduce what is SUSY current Lie conformal algebra. So let's see what is SUSY current Lie conformal algebra. So let's consider Lie superalgebra G, which has even supersymmetric bilinear form. So you can consider G is of type ABCD, but not like PQ types. And then consider G bar, and G bar is as vector space isomorphic to G, but this bar reverse the parities. So parity reversed vertex, parity reversed vector superspace. And then consider this T tensor G bar plus C of central part capital C. Then consider this capital lambda bracket like this. So it looks like very similar to ordinary current Lie conformal algebra. And C is, of course, in the center. This is called SUSY current Lie conformal algebra. And then to get SUSY affine vertex algebra, you will just take universal enveloping SUSY vertex algebra, and then take quotient by C minus K. This is called level K SUSY affine vertex algebra. So now I should explain then why this vertex algebra is called SUSY affine vertex algebra. I want to explain by comparing it with ordinary affine vertex algebra. So since we now in nk is equal to 1 case, let me just take D. So let's assume we have a SUSY vertex algebra here. Then how we get vertex algebra structure in this SUSY vertex algebra? This is easy. So here we have lambda bracket, capital lambda bracket, which is sum of lambda to the n psi to the j. J is just 1, 0 and 1, and a n j of b. And then here, you just look at this bracket and take the coefficients of lambda to the n and psi to the 1, a n 1 of b. And then take this take this coefficient, and then for the variable, so you will take just, sorry. So here we you just remove this psi here. Then you will get lambda bracket, and indeed, with this lambda bracket, you will get vertex algebra V. So let's see the SUSY vertex algebra here. So let's go back to the previous slide. So if you do A bar lambda B bar, then the coefficient of psi is -1 to the A times C times AB. So here I wrote down here like this. And for this one, you will get, so here by statistical linearity, you have psi here. But psi square is minus lambda. So if you take coefficients of psi, you will get just P of A, something like this. So we have, sorry, I forgot it. And then if you compute this one by statistical linearity, you will get, I'm not sure if it is plus or minus. Let's just write down like this. You can compute this one by just statistical linearity. So the conclusion is that for SUSY vertex algebra V, let's see. So affine vertex algebra. And here, SUSY affine vertex algebra. If you consider the map which sends A to D of A, then it becomes actually an inclusion. So injective vertex algebra homomorphism. So this is why we call this algebra by SUSY affine vertex algebra. So I introduced SUSY vertex algebra and explained what is SUSY affine vertex algebra. So now I can explain what is SUSY W-algebra. So setting is like this. We have finite simply superalgebra, and we require that this G has non-degenerate, even supersymmetric bilinear form. And here, S is subalgebra of G isomorphic to OSP 1, 2. Then the even part of S should be isomorphic to SL2, and I will write down like capital E, capital H, and capital F. And the odd part has like dimension 2, and it is spanned by small e and small f, and I will assume that HF is minus. And then, of course, G has at X eigenspace decomposition, and I will use notation, this n to be the positive part and n minus to be the negative part. Yeah, and then I also want to remark that for affine vertex algebra, in the previous slide, I used the lambda bracket when I want the like this, but from now on, I will use this parity. But actually, these two structures are isomorphic. But I just want to follow the physicist convention. So now let me introduce what is the ingredient for SUSY vertex W algebra. So first we have affine SUSY vertex algebra, and then charged free fermion SUSY vertex algebra. And this one is, I should say, this is charged free fermion Lie conformal algebra. And it is generated by phi sub n and phi to the n minus. And the lambda bracket is defined like this. It looks very similar to the ordinary W algebra. And we will consider new vertex algebra, C of G bar F K. F is the F here, and K is just constant K. And it is a tensor product of just this one and this one. And take an element D, which is which is an element in this new vertex algebra. And then, yeah, and then Q is operator on C, in the morphism of C. And you can check that Q is odd and Q square is equal to 0. And the definition of SUSY W algebra is like this. Just cohomology of this complex C and Q. This is the definition. So you can see the definition is quite similar to our ordinary W algebra. So the question is, what is classical limit of SUSY classical W algebra? So I think maybe many of you guys are more interested in SUSY quantum W algebra, but for me, I worked more on classical case. So I was curious what is the classical W algebra. So what I tried is just consider the symmetric algebra of like classical limit of affine SUSY vertex algebra, say affine Poisson vertex algebra. And also, since you have charged free fermion Lie conformal algebra, by taking supersymmetric W algebra, supersymmetric vertex algebra, you will get Poisson vertex algebra. So you can consider the Poisson vertex algebra, which is obtained by tensoring these two Poisson vertex algebras, and consider D, which is almost same as this one, but instead of normal ordering, I just use the ordinary just product. And then define classical W algebra as the cohomology of this symmetric complex and the operator Q. And then I decided to call it classical SUSY W algebra. And then indeed, I could see this classical W algebra is kind of Hamiltonian reduction of affine SUSY Poisson vertex algebra. So naively speaking, when I prove this theorem, I want to take element here, let's say a bar, and send it to just naively. Naively, I want to find this J sub A. And then actually I found, not I found, but I could see there is a building block, J sub A, and the analogous element in this quantum complex. There is some analogous element, and it is called building block. And I computed what is the bracket between JA and JB, and how this D acts on J sub A. And as you can see here, it actually, the bracket between J sub A and J sub B is almost same as the bracket of affine SUSY vertex algebra. Actually not similar, but just same. And also I want to emphasize that this K is same as the K in the affine SUSY vertex algebra. This is actually not true in ordinary W algebra theory. That is, I think, because the reason you get different K in ordinary W algebra theory is that when you compute the bracket between these two elements, by the weak formula, you will get some extra terms, and then make a different constant here. But here, somehow this becomes to 0, and you will get just K, the same K. This is the difference. So maybe I can say SUSY W algebra is a little bit easier than the ordinary W algebra in this sense. So anyways, the structure theory of SUSY W algebra is quite similar to the ordinary case. So you just break this the BRST complex into two parts, and then check this part is equal to just constant, and then see this one is just equal to the 0th part of the cohomology. Now, everything is almost same. So, and then you can say that every element in SUSY W algebra has a representative of the form like this. Just building blocks, derivatives of building blocks. And then here also, you can see the theorem is almost same as the ordinary case. The only difference is you have the number of free generator is dimension of G sub 0. For ordinary case, So generator, number of generator is dimension of G0 plus dimension of G1/2, right? But here you have dimension of G0 generators. And also, yeah, this part is also very similar. So yeah, if you take a basis of corner of at F here, you will get a free generating set, which has the form of like this. So now let me explain some examples. I will take G is equal to GLN plus 1 N, and F is odd principal. So here I wrote down some lengthy explanation, but what I wanted to say is if you write down this one, elements in this Lie superalgebra in matrix presentation, we usually write down like this: those N plus 1 even part and odd part. Instead of this, we used this kind of realization. So this part is even, odd, even, odd. Then you will finish with even. So if you use this kind of presentation, you will see Eij as parity I plus j. This is how we, the presentation we use. And here I wrote down explanation of this presentation. And then we consider the matrix A. So the entries looks like this. So this part, the upper triangle part is 0 or -1. And for the lower triangular part, this is just, this is D plus J11, E11, JE21, JE2n plus 1, 1, and D plus JE22, something like this. And then we consider column determinant of A. The column determinant is written as like this. And then we rewrite it as in the form of like this. Here W, so P is in this complex, and this D is the derivation part. Then the theorem is these coefficients W0, W1 to W2n plus 1 are actually belong to W algebra. And then by comparing to the theorem here, you can check that we really have the number of elements here is the same as the number of generators we should have, and so on. And then we eventually you will see that W1 to W2n freely generate W algebra associated with G bar and F. So here I wrote down simplest example, but let me skip this part. And then the most recent result is that for BCD type, for BCD type, we also have so BCD type. So G is A type, and G has odd principal. That means G is SL n plus 1 n. And G is BCD type, and G has odd principal, means that G is OSP 2n plus minus 1 2n, or OSP 2n 2n, or OSP 2n plus 2. So for this case, we showed that the classical case and quantum case generators can be found by column determinant formula. But for this, for the second case, we could not get for the quantum case, but for classical case, you still can get generators via column determinant for some matrix. And in this paper, we wrote in each case what kind of matrix we should consider, and then what is the explicit form of generators for this case. Okay, so I want to say about further questions. What do I want to know? So first thing is about superconformal vector. For affine SUSY vertex algebra, this is known. But for W-algebra, I think it should not be that hard, but not yet. I think it can be proved very soon, and it should be simple. But also for the classical case, what is known that in ordinary classical case, we know that there is conformal vector which admit primary decomposition. But for SUSY case, I think I can find just random, just any superconformal vector, but still I don't know. Also in this case, we can find the superconformal vector which admit this primary decomposition. That is one question. And also, I want to know if this SUSY W-algebra can be obtained by some kind of known vertex algebras. So I explained that if you have a SUSY vertex algebra, you can easily induce vertex algebra, because actually SUSY vertex algebra is a vertex algebra. But yeah, we know lots of, not lots of, but we know vertex algebras, but I'm not sure what kind of vertex algebra, what kind of well-known vertex algebra can be related to this SUSY W-algebra. That is another problem that I can suggest. And then, yeah, since I have been working on integrable system, I'm doing some work on super integrable system and SUSY Poisson vertex algebra theory. Yeah, so yeah, I think that's it.
Thank you so much. Let me stop the recording.
Thank you.